Thus far, when I've been discussing time value of money, I've been assuming that interest was only paid once a year. Well, there are quite a few different types of investments that pay interest more often than once a year. So what I want to do is address the idea of the compounding frequency. And that simply means how often per year is interest paid. That impacts our rate and our time period when we look up a number on the interest factor tables. So let's work a fairly simple problem. And let's say I deposit $100 at the beginning of, or let's just say right now. So today, in an account that pays 8% interest annually, but it's compounded quarterly. And I'd like to know the value in this account at the end of 2 years. I'm actually going to set this up in Excel because I can work it a little bit faster. You don't need Excel to calculate this answer, but it'll just be quicker for me to type it that way. Sorry, I didn't have this open and ready. Okay, so what I'm going to do here is put the beginning of the year, or beginning of the quarter balance. And then I'll put interest earned, and then the end of the quarter balance. And actually, I'm going to zoom in on this so y'all can see that a little better. And just hopefully quickly figure out how to wrap those so they look a little better. And yeah, I see I spelled balance wrong. Okay, so, and also what I want to do is track the quarter. We're keeping our money in for 8 quarters, so I'm just going to go quarters 1 through 8. And the beginning of the first quarter's balance is that $100 that I put in there. Now the interest that I earned, it's paying 8%, but it's compounded quarterly. So if I take 8% and divide it by 4, because there are 4 quarters in the year, that will tell me my quarterly interest rate. And in Excel, I just have to put an equal sign in front for it to do the math. So I'm actually getting paid 2% interest every quarter. So at the end of the first quarter, they'll take my beginning of the quarter balance and they'll pay me 2% on that. So I'm going to go 2% times the beginning of the quarter balance, $100. So I earned $2 in interest that first quarter. So at the end of this first quarter, I take the original 100, I add the $2 in interest that I earned. That's the balance at the end of the first quarter and the balance at the beginning of the second quarter. So I'm just going to pop this 102 over to here. The second quarter, I'm again going to earn 2% interest, but I won't earn it on $100 this time. Instead, I'll earn it on $102. So I earned $2.04 in interest, 4 cents more than I earned the quarter before. That extra 4 cents is the interest that I earned on this $2 in interest that I earned the quarter before. So I'm earning interest on the interest and on my original 100. And I'm just going to drag that formula down because what it's doing is taking this beginning of the quarter balance, adding the interest I earned to give me my end of quarter balance. At this point, I can just drag all these formulas and it'll copy them. So I will end the 8th quarter, the second year, with $117.16. There is a quicker way to find that answer using the future value of a single sum formula. And I'm going to go ahead and type it out one more time. I'll take the present value of the single sum and I'll multiply by that interest factor. And I'm going to go ahead and type out the interest factor. It's 1 plus I raised to the exponent of time, or n. Oops. And again, I'm just making that the exponent. What we had done before is we'd made our n 2 for the 2 years, and our I was 8 for the 8% annual interest. This time you don't do it that way. You make your I the quarterly rate, 8 divided by 4 quarters, so 2%. And I need to make it a decimal. So again, I'm getting paid a 2% quarterly rate. And then my n, I need to make 8 because it's 8 quarters in 2 years. So if I take 1.02 and I raise it to the power of 8, that gives me 1.17. Just going to type that out. 17. That's my interest factor. So to find the future value of my single sum, I take my $100 and multiply it by that interest factor of 1.17, and that gives me $117.17, which is what we got with the slight rounding difference over here in Excel. But I could also look up this interest factor on the interest factor tables, but rather than using an I of 8 and an n of 2, I use an I of 2% and an n of 8. So we're going to go to the appropriate interest factor table and find what interest factor we discover at the intersection of this rate and this time period. It should be 1.17. The proper interest factor table to use is the future value of a single sum. So go to the I of 2. I'm going to zoom in a little. I'm not sure how well you'll be able to see it on the video. So go to an I of 2, go down to an n of 8. There's that 1.1717 interest factor. The process works this way for every single type of time value of money question. If you've got compounding more often than once a year, always take your interest rate, divide it by the number of compounding periods in a single year. You'll notice I didn't take this 8% and divide by 8 quarters, because there's not 8 quarters in a year. There's only 4 quarters in the year. The fact that the money was kept in for 8 quarters is dealt with the adjustment to your time period, your n. So always take your interest rate divided by the number of interest payment periods in a single year, and then take your time period and multiply it by how often interest is paid in a single year. So since interest was paid quarterly, I took those 2 years, multiplied it by 4 quarters in a year to get the n of 8. Doesn't matter if you're working with annuities or single sums, present values or future values, you must make this adjustment for all of them. One other thing I want to talk about is the effective annual rate calculation. And there's no table that you can use to look this up. You're just going to have to work with the formula. I like to call it EAR because it's kind of funny. But to find the effective annual rate, what I would do is take 1 plus what they call the nominal rate, and then you take this nominal rate. The nominal rate is also what they call the stated rate, and I actually like calling it stated rate better. But on calculators, if you have a financial calculator, they're going to call it the nominal rate. But you take this stated rate and you divide it by the number of compounding periods in 1 year. So stated rate divided by the number of compounding periods in 1 year, add that answer to 1, and then raise that answer to the number of compounding periods in 1 year. Then, we're almost done. That's a exponent, so I just want to make sure you realize that. And then once you have that answer, you subtract 1 from everything. The answer is the percentage, the effective annual rate. So let me tell you why this is important. Let's say you're evaluating certificates of deposit, and the first one that you've looked at is offering you 1.5% with, we'll say, compounded monthly. So they're going to pay you interest every month, not 1.5% every month, but 1.5% divided by 12 every month. And another CD is offering 1.6%, but it's only compounded quarterly. And actually, because I want to prove a point, I'm going to lower this to 1.52 and hope that what I'm trying to show you occurs. Because these have different compounding periods, months versus quarters, I cannot do a straight comparison and say CD2 has the higher stated rate, 1.52, compared to CD1, which therefore CD2 is better. I have to equalize the two. The fact that one pays interest quarterly, another pays interest monthly, and they have different stated rates. To equalize the two and give them a fair comparison, I have to calculate the effective annual rate. So I'm going to do that for both of them. So for CD number 1, I'm going to kind of work it in a strange way, but I'm going to take that stated rate of 1.5%. I have to convert it to a decimal. I'm going to divide by the number of compounding periods in 1 year because they're doing monthly compounding with CD1. It's 12. Then I'm going to add 1 to that. Next, I have to raise all of that to the power of the number of compounding periods in 1 year, which would be 12. Again, that's an exponent. And then finally, once I calculate all of that, I subtract 1 from the entire thing. And I just want to emphasize, I do all of this. I'm still learning this recording software, and unfortunately it's kind of being a bugger. It's covering my highlighting tool, but there we go. So I need to do the entire amount in the order of the parentheses that I've highlighted in yellow, then I subtract 1 from everything. So let me do all of that. So I'm going to take 0.015, divide that by 12, get that answer, add 1 to it, then raise it to the power of 12. That gives me 1.015, and I'm going to carry it out to a few decimals. Then I'll subtract 1 from it. That'll give me 0.0151036, or 1.51035, or 6. That's what I meant to say, percent. Now, right away, I can tell, well, actually, let me backtrack a little bit. When there's compounding that's more often than once a year, the effective rate, that we'll calculate with this formula will always be higher than this stated rate. So I know when I calculate the effective rate for CD number 2, it's going to be higher than 1.52. So the effective rate for CD1 is already lower than the stated rate for CD2. So I already know CD2 is my better choice. But I'm going to go ahead and calculate the effective rate for CD number 2. I'm going to just copy this so I don't have to do the parentheses and everything all over again. I'm just going to change the relevant information. So for CD2, it's not 0.015, it's 0.0152. And the divisor isn't 12, it's 4 because it's quarterly compounding. And then the exponent isn't 12, it's 4, again, because it's quarterly compounding. So crunching this, I'm going to take the 0.0152, divide that by 4, add that answer to 1, raise all of that to the power of 4. That gives me 1.0152868. Then I would subtract 1 from that. Gives me 0.0152868, or 1.52868%. I would want to choose the CD with the highest effective rate, so that is CD2.